It's physics time.
Oh! It is?
Yes. Hey, Aurora, what do you have there in your hand?
Well, I have some blueberries, Leighton. Why do you ask?
I ask because we've been learning about pendulums in class, and I wanted to see what variables affect the period of a pendulum. I know that length does, and amplitude does not. But I wanted to see if mass does, and I wanted to use a small incremental mass variable to test it.
You mean like blueberries?
Exactly.
Wow.
And I have a pendulum,
That makes one of us.
and you have blueberries.
That makes one of us.
And I also have this large bowling ball-shaped object.
What is it?
A surprise tool that will help us later.
I see. Leighton, since this is your experiment, what is your hypothesis about the effective mass on a pendulum?
Well, since the pendulum will enter simple harmonic motion at a small enough amplitude, we know that there must be a restoring force bringing the pendulum back down to equilibrium, which in this case is gravity.
Oh, I see what you're saying. So you're saying that because the force restoring is equal to Fg, and Fg is equal to mg, right? Right? Get this. The mass, boom, has a direct effect on the force restoring, which in turn has a direct effect on, say it with me, the period of the pendulum. That's absolutely bonkers brilliant, Leighton.
Actually, since no external force does work on the pendulum, then mechanical energy is conserved. And since the motion of objects, and therefore their period, is based on mechanical energy, we can look at the equations. At the max displacement, all of the energy is potential, mgh. And at the minimum displacement, all of the energy is kinetic, 1/2 mv squared. Since mass cancels out, and the period is based entirely on mechanical energy, we know that mass does not affect the period.
Well, I suppose we'll have to see who is correct. It's time to test.
We'll start with some blueberries, then move on to some other objects with a greater mass to see how doing so affects the period. We will use a constant length of pendulum and angle of displacement. Let's test. All right, the first batch, with a mass of 0.567 kilograms, has a measured period, averaged over 3 trials, of 4.07 seconds. Add the second batch.
Second batch?
There is no second batch, is there?
Theoretically, there are 5.
That's fine. We can add other things like...
A textbook.
So as long as we keep track of the masses we are adding, we can add whatever we want. All right, the textbook, with a mass of 2.415 kilograms, has a measured period, averaged over 3 trials, of 4.05 seconds.
Darn, this isn't looking good for my hypothesis. Let's add something much more massive to see if that has an effect.
I like your thinking. Let's add our surprise bowling ball-shaped tool that will help us in what was later, but is now the present.
Is it a bowling ball?
You know me so well.
So, the bowling ball of mass 6.93 kilograms has a period of...
4.04 seconds.
Wow. It looks like we experimentally proved my hypothesis wrong because I didn't consider the equations for mechanical energy, which, when examined, show that the mass of the pendulum cancels out of those equations and therefore does not affect the period.
Exactly. Now, do you know what time it is?
Blueberry eating time!
Who knew blueberries could be so useful?
Nobody.
They are a superfruit.
That was some fun physics.
It was. Do you want to do it again sometime?
Yeah. Yeah, that'd be fun. You know, I hear that they're gonna make blueberries the national fruit.